Hello, this is Mr. Collier. Today we're looking at vector equations of lines. Okay, so up till now our vectors indicate direction and magnitude, but we want to be able to describe a line using vectors. So here's how we do it. This is 1 point on the line, the position vector, 1 point on the line, and this is what we call the direction vector. Okay, that's the direction that's pointing in. Okay, it's kind of like y equals mx plus b, right? Where the direction vector gives you the slope. You go up, you go right 2 and up 1. That's basically the slope of the line. And 1, 2 is any point on the line. Doesn't need to be the y-intercept, but any point on the line. And this will describe every single point on the line. Okay. So like if we take a look here, the point, this is the equation down here. So if you substitute in different values of t, basically you generate points on the line. If you plug in t equals 0, you get this point right here, right? If you plug in t equals 2, you get, or t equals 1, you get this point right here. And you plug in t equals 2, you're going to get a 4, 2 here. You add together, get the 0.55, which are all points on this line, right? Okay, so you plug in t as a fraction, you get some points in between. So this equation does indeed describe every point on this line. Okay, so as always, the initial or any point on the line and the direction vector. Alright, this is what it's looked like. It looks like in kind of condensed form. R is the vector xy or xyz in 3 dimensions, so it represents a column vector like that, and A is any point on the line, and B is the direction vector. Okay, so a line passing through 1, 2 in this direction here, you can write it like this. Okay, and sometimes we just write it like this as well, so that when we're solving equations or converting the form. Okay, so this is called the vector equation of a line. Another version is called the parametric form of the line, where we just write out the separate components: x equals this, y equals that, and z equals that. So it means the same thing, just looks a little bit differently, right? Okay, so we find the equation of a line which passes through this point. So I have 2 points, so that's useful. And we need to find the direction that this vector is going in, so we need to find the vector AB or the vector BA. Gives you the direction. So BA, we do B minus A, so we're going to have the vector 2 minus 1 is 1, 3 minus 0 is 0, negative 1 minus 2 is negative 3. So that's the direction vector, so you can say the equation of the line is 1, 0, 2 plus t times the direction vector, which is 1, 3, negative 3. Or you can use this as initial point, or any point on the line. And even the direction vector could be a different vector, like you could use negative 1, negative 3, and positive 3, or 2, 6, negative 6, as long as it's going in the correct direction. Okay, next is this point on the line. To check if the point is on the line, you can set it equal to this line and see if that actually works out. Okay, so if you solve you could solve for the x components. 3 equals 1 plus 1t, so t equals 2, right? And then you can see if it matches the other two. But if you plug in t equals 2 into this whole thing, you get, well, you're going to get the 3, obviously. And you plug t equals 2 here, you're going to get 6. You plug in t equals 2 here, you will get 2 times negative 6. 2 times negative 3 is negative 6, plus 2 is negative 4. So yes, it is on the line. Okay, if one of those didn't match, then it's not on the line. Point 3AB also lies on the line, so let's find A and B. So you can set it equal to our line, which is 102 plus t times 1 negative 3, 1 3 negative 3. Okay, so you can figure out what the t value is by solving the first equation. T equals 2, and then you can just plug it in and get the other values. Actually, it's the same as the previous question, I believe, so it's pretty much the same thing. This one here, these represent the same line, so let's check and see if that's the case. You can see that the lines are definitely parallel because it should be like R1 and R2, we usually call it like that. Okay, so the direction vector of R2 is a scalar multiple of R1, so they're definitely either parallel or the same line, right? Now to see if they're the same line, you gotta see if they contain any points in common. So we can just test to see if, for example, 2, 1, 3, if that's on R2. So let's test to see if that is the case. Alright, so you can solve for S in the first one. So S equals 3 over 2. And so then if we plug in S equals 3 over 2, we get negative 1. Well, we know what the first one's going to be. The first one's going to be 2. Second component is going to be negative 5 plus 3 over 2 times 4, and the last one's going to be 0 plus 3 over 2 times 2, which equals 2, and this one's going to give you 6 plus that equals 1, and the last one is going to give you 3. So yes, it is on the line, and that's why they are the same line.